Hello guys, welcome back to the YouTube channel of The Concept Guy, and today we are going to look at the fluid mechanics basics and how to deal it with it in last minute. And here we have the book McCabe Smith, which is one of the best book for fluid mechanics. It's named as Unit Operations of Chemical Engineering. We have the fifth edition with us, so you can actually refer to it. So we're gonna post more videos on other topics, but for this time let's just start the fluid mechanics. So I hope you have been facing a question that what to study in GATE exam for fluid mechanics. So here we have all the topics for GATE exam. There are majorly 6 topics that we need to focus upon, and first is application of Bernoulli's equation, second equation of continuity, third Venturi meter, fourth orifice meter, Hagen-Poisson equation and the friction factor, and lastly the drag coefficient. So questions come mainly from these topics in GATE exam, and now we are going to look at how to study it in general, like for semester exams and other exams. So let's begin. So let's just move on to the fluid mechanics section, and before moving on, let's get to the contents. So mainly for us, the 4th chapter, the 5th, the 7th and the 8th, these are the most important chapters to actually go through fluid mechanics for undergrad. So let's begin upon the basic thing first, and here we have it on in the first topic, first chapter, where we will see that GC and J are included. These are included for the use with FPS units, and for SI systems GC is actually 1. So remember that. Next we move on to the first chapter of fluid mechanics, that is statics, fluid statics. And so we have some of the basic equations like the pressure differential upon area, which comes out to be to this equation. So you can actually derive it very easily. This is what the fluid statics for centrifugal field. So they have given a particular R1 radius to R2 radius. The fluid is between this, and for any R radius and dr element with a height of b, so the force is equal to, so force is equal to mass into acceleration, and mass here is density into volume. Just these two equations, and then we take pressure is equal to force upon area, and finally the pressure drop over the entire ring is actually integral rho omega square rho r dr upon gc. Gc is actually 1 if it's SI system. Next we move on to inclined manometer. It is used for to measure very low pressures, and here we have the decanter, gravity decanter, in which liquids of 2 different densities come as feed, and the lighter one has ZB depth and the heavier one has ZA1 depth, and the final outlet has ZT length, depth, and heavy fluid and light fluid are separated. So we just put the hydrostatic balance, which is one of the simplest balance, rho GH. So H is here, the different ZA1, ZBs and rho, and because G is same, so it cancel out in this equation. So finally we arrive at this particular equation. ZA1 is equal to ZA2 minus ZT bracket rho B by rho A upon 1 minus rho B by rho A. The next important thing is potential flow. Potential flow is the flow one that is incompressible, zero velocity. It's a good flow irrespective of the boundary layer. So what is boundary layer? Boundary layer is the effect of the wall, the solid boundary over the flow. Next we move on to the Newtonian and non-Newtonian fluids. Newtonian fluids which obey Newton's law of viscosity. So the shear rate is directly proportional to the velocity gradient. But for non-Newtonian fluids, it is proportional to the velocity gradient to the power n. When n, so if we plot shear stress and velocity gradient, if n is greater than 1, then it is a shear thickening fluid, that is dilatant. And if n is less than 1, then it is shear thinning fluid, that is pseudoplastic. Now both these fluids are actually time independent. If we move on to the time dependent fluids, then these are thixotropic, which thins, time dependent, yes, and rheopatic, which thickens, time dependent, yes. So this is the Newton's law of viscosity. And let's move on to the next topic, which is, here we were talking about flow consistency index and flow behavior index, K dash N dash, for non-Newtonian fluids. Let's move on to the next topic, and next important topic is the formation of boundary layer. So if a fluid stream is coming with the velocity u, so due to the presence of solid wall, the fluid near the wall will have zero velocity, and while we go up the wall surface, the fluid moves with a greater velocity. So a boundary layer is formed. Now slowly the boundary layer forms, and when the fluid enters the pipe, and when after the whole interaction we get a fully developed flow. There is a particular transition length for laminar and turbulent flow for the flow to be fully developed, and for laminar it is given by this equation, and for turbulent flow it is actually independent of the Reynolds number. Like here it is dependent for laminar, but for turbulent the transition length is independent of Reynolds number and is about 40 to 50 pipe diameters. So this is how the fluid enters from one side of the pipe and moves as a parabolic curve due to boundary layer. Boundary layer and wake formation. So these are eddies that are formed, and this is wake vortices. Next we move on to the next chapter, fourth chapter, which is one of the important chapters. Here we have the continuity equation of continuity, which is one of the most important equations, and it talks about the conservation of mass and mass flow rate. So V bar is Q upon S. V bar is the average velocity, which is upon the flow rate, total flow rate, volumetric flow rate upon the area, cross-sectional area. So mass velocity is mass upon time upon area, denoted by G. In this example, we have mass entering and dividing into two streams. So just put the mass balance, volumetric mass flow rate, and next we have momentum balance. dm upon ds is rho u square. So we can actually get it from the momentum upon time upon area, and it's equal to rho u square. We must remember this. And for the momentum correction factor beta, it is nothing but 1 by s integral of u by v bar whole square ds. Remember, it is square for beta, and it will be cube. The power will be cube if it is alpha. Alpha is the kinetic energy correction factor, which we will surely get in Bernoulli's equation afterwards. So for Bernoulli's equation, to derive it, we generally consider a pipe, a tube, in which the flow enters at P pressure and exits at P plus delta P from a larger surface area, and there is gravitational flow and there is also wall effect, and we generally put a force balance. So the force balance is nothing but the pressure difference into area and the wall effect and the gravitational effect. Here we have the pressures into cross-sectional area. Next we have the force of the wall, and lastly the gravitational force. So we come up to the final Bernoulli's equation. So Bernoulli's equation, this is for without friction. What if we consider friction and the velocity changes that are supposed to be due to the friction, and so we have some correction. So for the kinetic energy correction, we have a particular factor, that is alpha. I've said it is to u by u bar to the power cube, unlike the momentum correction factor where we have seen it is square. So if friction HF is added as a correction to the Bernoulli's equation, then the equation seems to be like this. Also there is skin friction, where friction is generated in unseparated boundary layers. Boundary layers are unseparated here. And from form friction, there is a wake formation, and friction appears due to a position or shape of this solid. So the pump work in Bernoulli's equation, so let the work of the pump is WP minus the friction is equal to efficiency of the pump into work of the pump, and we just put it in the Bernoulli's equation like this. So this is the pump efficiency into work of the pump, that's added to the Bernoulli's equation. Next we quickly move on to the next set of topics in chapter 5. Chapter 5 mainly deals with the force balance in a pipe, where P is from the entrance point and P plus dP is the exit point pressure, and there is a wall shear let's consider dl length of a disk, and we finally arrive at this equation while doing a force balance, a simple force balance. So let's remember this equation and let's put it with the Bernoulli's equation. Because the pipe is horizontal, so we can say the change in height is 0 actually. And we also take the two kinetic energy terms cancel out each other. So finally we have del P upon rho is HFS. Here we put it, we use equation 5.2 and equation 5.4, and combining we get HFS. So now we introduce a new term, the friction factor F, which is tau W upon rho V square by 2, rho V square by 2. We have seen it to be like an energy unit, and tau W is a pressure unit. So tau W is similar to pressure upon energy, and it's the friction factor. So we put the values of tau W and the DL values, and from the above equations 5.2 and 5.4, and we get final F. Next, this is one of the important correlations and the most important equation, Hagen-Poisson equation, which is this equation. We must learn this equation also. It's mostly used in many questions, and also the F comes out to be 16 by NRE from using the Hagen-Poisson equation. Next, we quickly move on to the next chapter, because we are considering the main important topics, and here we have vena contracta. So vena contracta is that portion where the fluid first converges then diverges out. So there's a different contraction loss coefficient and various loss coefficients. You can check them out. And finally, if we move on to the next chapter, that is chapter 6, compressible fluids. Here the main topics are actually these three cases. One, when there is a nozzle, a divergent section, and the convergent section. Second, adiabatic and thermal insulation. And lastly, we are heating and there is a friction section. Not much to go into this chapter. We finally move on to the next chapter. Unit operations and fluid mechanics are very vast topics, so we are just looking at to how we can actually learn it and grasp it briefly. So there are two types of drag, wall drag and firm drag. This is the pressure force and this is the wall force, wall drag. And here we have the drag coefficient finally, which is force upon area, that's pressure upon rho u square by 2. So it's pressure upon energy, kind of the thing that we have seen with F, friction factor, but the drag factor appears when there's a drag force acting on an object placed in a fluid like this sphere, and it gets a drag force. So moving on to next topic, we'll move on to fluidization. Fluidization is a vast topic, so I will just suggest you to get a knowledge of how fluids behave in the voids in the bed, and finally we get the equation, the Ergun equation. So these are the equations. The Ergun equation, and so this second term is actually the Burke-Plummer's equation. And moving on to the next topics, one of the most important thing in fluid mechanics, chapter 8, transportation and metering of fluids. So here what we are going to see is that the main thing is suction, lift and cavitation. Cavitation is a process in which we have to make a particular difference, balance the pressure so that the flow is steady and there is no vaporization. And so NPSH is a very useful term in pressure balancing of a pump inlet, and it is given by this equation. We generally neglect the velocity head at the pump inlet, but if we are taking it, then we have NPSHR, which is the minimum required net positive suction head. So NPSH is a very critical topic, and next we move on to the pumps. For pumps, this is a centrifugal pump diagram. So at the center, fluid comes in and it moves with the centrifugal force and finally exits. We next move on to the characteristic curves, head capacity relations in the pump. So these are total power and the fluid power, and basically we'll move on to the pump section is over for now. The Venturi meter is an important topic, and here we see a convergent section, then the divergent section, and mainly if we just do again the hydrostatic balance, then we come up with the Venturi coefficient. What is beta? Beta is the diameter ratio. And so what we are doing actually, V square upon 2, that is, we are applying the Bernoulli's equation. This is a consequence of Bernoulli's equation here, and then putting it all together, and with beta we get to arrive at this equation, and finally we put a CV to account for alpha A and alpha B, and we account it by replacing with CV, which is the Venturi coefficient, which varies for 0.98 and 0.99 for larger sizes. The mass flow rate, the same thing, rho S into V bar. So V bar B we have got from equation 8.34, and we put up to calculate the mass flow rates, and volumetric flow is the same as mass flow rate upon rho. The pressure recovery in Venturi meter is actually more than the orifice meter, a good pressure recovery, because Venturi meter were frictionless, then the pressure leaving with the would be exactly equal to the entering fluid pressure. Venturi meters are actually costly to construct, and we cannot change the nozzle diameter, but for orifice we have many advantages, and because of this we generally use orifice because the throat diameter could be changed. And one disadvantage of orifice is that there is low pressure recovery because a lot of pressure is lost in this throat. So this is the percentage of maximum pressure difference. This is the diagram of orifice meter. We put up orifice blades, and in the same way we derive the UO, the velocity through the orifice. CO is the orifice coefficient, which varies upon 0.161, and so this is the basic equation derived from Bernoulli's, again similar to the Venturi meter. And the pressure recovery in orifice meter, due to large friction losses, pressure recoveries or in orifice meter is generally poor. Anyways, it's easy to operate at orifice meter because we can change the throat diameter. This is a Rota meter where a drag force comes from the downward side to the upward and the gravitational force, and these are balanced, and we finally measure the flow rate. So Rota meters, area meters, and they are flow rate measuring devices. So there are also some meters like the Pitot Tube, which is an insertion meter, and for Pitot Tube it generally gives us the velocity at point B in this diagram, and we can find it out with a correlation. Not much important, but just to know it in a brief way. So I hope you like the video. Please like, share and subscribe.